In this module, we're going to talk about weak bases and some fun things we can do with them. All right. So, if a base is not a strong base, and I gave you a list of the 8 common strong bases anyway, if it's not a strong base, it's a weak base. And not all bases contain the hydroxide ion. A lot of weak bases have no hydroxide ions in them. But when you put them in water, oftentimes they do produce it. For example, let's look at ammonia and how it's a weak base. If you put ammonia into water, the nitrogen atom in the ammonia molecule has a lone pair of electrons. If you draw the Lewis structure, accepts a proton from water, which donates a proton. Water being acting as an acid in this sense, creating the ammonium ion and hydroxide. So this is a base. The K, just like we have a Ka for an acid, we have a Kb for a weak base. And it's really just the equilibrium constant for this reaction. It's the equilibrium expression. So it's the concentration, in this case, the concentration of ammonium times the concentration of hydroxide divided by the concentration of ammonia. And it just so happens that for ammonia, the Kb is equal to 1.8 times 10 to the minus fifth. Again, you don't have to memorize any Ks, no Kws. Well, excuse me, yes, you have to know Kw, but you don't have to know Ka or Kbs. So this is a table of some, just a real few Kbs. Same idea as with the Kas. The larger the value of Kb, the stronger the base, the more hydroxide ion there is present in solution at equilibrium. We can also define a pKb just like we can a pKa. Just take the negative log base 10 of these numbers and we get the pKbs. And just like with pKas, the smaller the pKb, the stronger the base. So let's get right into it. Now we want to calculate the pH of a solution whose concentration of ethylamine, which is one of those bases I showed you, is this number right here. All right, so there's the equilibrium reaction. There's the Kb expression. And I just looked up in the table this number right here. So you look it up. What we're going to do, is we're going to use this expression to find the concentration of hydrogen ion indirectly, and thus negative log base 10 of the hydrogen ion concentration is the pH. So how are we going to get at that? The only way we can get at that is through hydroxide. Remember, if we know or can find the concentration of hydroxide, well, then it's easy to get the concentration of hydrogen ion and consequently the pH. So our first goal is to find this guy right here. So we're going to set up an ice table. Now we started with 0.0519 molar ethylamine, no ethylammonium, and approximately 0 hydroxide. Remember, this is water, so there's initially, before we put anything in, there's 1 times 10 to the minus 7th moles per liter of hydroxide. We're going to assume that we can neglect that, but we'll check it at the end. Our change is minus x plus x plus x. At equilibrium, we have these guys, and there's our equilibrium expression. But we know what it's equal to, Kb. All we're going to do now is we're going to solve for x. That'll be the hydroxide ion concentration. So it ends up that if you, and you should do this at most every time, assume that x is a lot less 0.0519. When you do, you'll find that it does not satisfy the 5% rule. So what? So we have to use the quadratic equation. Big deal. Well, there it is. Solve it. Get 2 roots for x. We can throw this guy out immediately. It's nonsense. A negative root just does not make sense in this situation. So now we have one that makes sense, x, and check in our assumption that it was a lot bigger than the initial concentration of hydroxide from the dissociation of water, 1 times 10 to the minus 7th molar. Yeah, sure it is. It's orders of magnitude bigger. So we know x, which means the concentration of hydroxide. Remember, we want the pH, right? Well, the hydrogen ion concentration, remember, hydrogen ion concentration times hydroxide ion concentration is equal to Kw, which is 1 times 10 to the minus 14th. By the way, for all of these problems, we're always going to assume the temperature is 25 Celsius so that we know Kw. If it were some different temperature, we'd have to tell you what Kw is at that temperature, and we're just not going to worry about that. So anyway, we solve for the concentration of hydrogen ion, get about 2.0 times 10 to the minus 12th molar. pH is just negative log base 10 of that, which is 11.71. There you go. Now, there's another kind of calculation that we commonly do. If we know the pH of a solution, we can get Ka and Kb from that. And that's really nice because we can just stick a pH probe into a solution and measure its pH, and bam, we know the Ka, Kb. So let's use an example to illustrate how we do this. Okay, so let's say we have a 0.398 molar solution of some weak base, doesn't matter what it is, and we measure the pH and it's 9.44. What's the Kb of this base? Well, pH is 9.44. Remember, the hydrogen ion concentration is 10 to the minus pH. Plugging in, we get about 3.6 times 10 to the minus 10th molar. Using the Kw expression, hydroxide times hydrogen equals 1 times 10 to the minus 14th, we get the concentration of hydroxide, 2.8 times 10 to the minus 5th molar. Set up our ice table, and now here, this represents the base reacting with water. This represents the conjugate acid of the base, and there's hydroxide. So 0.3980, approximately 0, minus x plus x plus x. And so we have at equilibrium these guys down here. Plug into the equilibrium expression. But now, see, we knew x to begin with, because that's just the concentration of hydroxide, which we calculated. We plug this in, we calculate Kb. It ends up as 1.9 times 10 to the minus 9. Really nice, really nice. All right, so last thing in this module. It ends up, you're going to see right here, it's pretty cool too, that there's a relationship between Ka, Kb, and Kw, where if Ka is for some weak acid, Kb is for the conjugate base of that acid. So these are related for a weak acid and its conjugate base. So let me show you why that is. So this is a generic reaction, equilibrium reaction for a weak acid. Ka looks like this. And okay, now I'm going to use the conjugate base of this acid, which is A minus. It, acting as an acid in water, would just be pulling a proton or accepting a proton from water to make the conjugate acid and hydroxide. Kb for that looks like this. Now watch. If we just multiply Ka times Kb, look what cancels. And what's left over? Concentration of the conjugate base cancels. The concentration of the acid cancels. All we have left is hydrogen ion concentration times hydroxide ion concentration, which is Kw, right? So the thing to get out of this is Ka times Kb is equal to Kw, but remember that Ka and the Kb are for a weak acid and its conjugate base, or a weak base and its conjugate acid, same thing. So real quickly, how to use that? Let's say we know Kb from that example that we worked a little while ago. 1.9 times 10 to the minus 9th. We found that. What's the Ka for the conjugate acid of that weak base that we dealt with? Well, just plug into that expression I just showed you, and we find it's 5.3 times 10 to the minus 6th.